In this movie, we will introduce advanced NanoLabo, an integrated GUI for nanomaterials, developed by Advanced Soft Corporation. Also, we will show demonstration of DFT calculation and molecular dynamics with advanced NanoLabo. The structure of this movie is as follows. Firstly, we will introduce features of advanced NanoLabo. Secondly, we will demonstrate how to execute DFT calculation of silicon single crystal on advanced NanoLabo. Then, we will demonstrate how to execute molecular dynamics calculation of copper single crystal on advanced NanoLabo. Finally, we will explain product information. Besides, links of each chapter in the description is available. Please note that you can watch articles of analysis cases and demonstration movies of advanced NanoLabo from the link in the description. Now, we will introduce features of advanced NanoLabo. Advanced NanoLabo is an integrated GUI for nanomaterials analysis via first principles calculation and molecular dynamics. The available solvers on NanoLabo are followings. Advanced Phase, which is first principles calculation software developed by our company. Quantum Espresso, which is open source software for first principles calculation. And LAMPS, open source software for molecular dynamics. Main features of NanoLabo are followings. On NanoLabo, you can search and download structure files from the Materials project, an online database. Settings of calculation on NanoLabo can be done extremely easily. NanoLabo has useful and various modeling functions. NanoLabo visualizes calculation results instantly. Moreover, NanoLabo can train neural network potentials when cooperating with advanced NeuralMD, which is developed by our company, and execute molecular dynamics using the trained neural network potentials as force field. NanoLabo will solve these problems. If you are interested in DFT calculation or molecular dynamics but feel hesitant to begin, you can execute calculations immediately on advanced NanoLabo. If you are struggling to editing input files, you can edit them on GUI easily, and default values are set automatically. If you have difficulty to create files of complex structure, diverse and easy modeling functions are implemented on NanoLabo, and enable you to create complex structures such as interface models and polymer models immediately. If you can't be bothered to visualize results on log files, you can visualize results on NanoLabo instantly. We show the list of main functions of NanoLabo version 2.8 here. Various modeling functions and many calculation functions are available. For LAMPS, you can use classical fields, general force fields such as Open Catalyst and M3GNet, and neural network potential trained by advanced NeuralMD as force field. Furthermore, visualization functions, job submit functions, and cooperation functions with Python are available. New feature of version 2.8 is Jupyter interface for NanoLabo. This interface enables you access Jupyter Lab from NanoLabo. You can send and receive structure files between NanoLabo and Jupyter Lab interactively. You can use this function without extra charge until July 31, 2023. As the first demonstration, we show how to execute DFT calculation of silicon single crystal on NanoLabo. Firstly, I search and download silicon structure file from the Materials project, an online database. Secondly, I set calculation conditions of self-consistent field calculation and structural optimization. Thirdly, I convert the crystal structure into primitive cell by modeling function. Then, I execute structural optimization and visualize the results. Finally, I calculate density of states and band structure of the optimized structure. Now, I search and download the silicon structure file from the Materials project, an online database. From the Materials Finder, you can search structures on Materials project, which is Inorganic Crystal Database, and PubChem, which is Organic Molecule Database. So, I enter SI in Materials Finder. Then, many structures include only silicon atoms on databases are displayed in several seconds. There are about 40 structures including only silicon atoms. I select MP149, which is diamond structured. Detailed information of each structure can be viewed using the Materials project link in the context menu. Then, I double-click MP149 and open the project. On NanoLabo, you can view the structure like this. I save the project from the menu on the bottom left. I save this project as Demo①. Then, I set calculation conditions. On the right of the screen, you can set various calculation conditions. From the menu on the bottom right, you can choose geometry settings, SCF calculation, structural optimization, first principles molecular dynamics, DOS calculation, band calculation, moreover, NEB method, phonon dispersion, phonon mode, JPA, SAFs, and time-dependent DFT calculation. On geometry, you can edit structure files. To be precise, settings of cell, pseudo-potentials for each element, and positions of each atom are available. NanoLabo offers not only standard settings on geometry but also advanced modeler functions which will be introduced later. From SCF of the menu on the bottom right, you can edit SCF calculation conditions. On Standard Setting tab, you can set cutoff for wave functions, number of K points, smearing and so on. The already entered values are set by NanoLabo automatically. NanoLabo decides suitable values for each structure file, so you don't have to enter the values for standard calculations. This is the same for values of other settings and pseudopotential files. On Electronic Optimization tab, you can set diagonalization method of wave functions, mixing rate of charge density and so on. On XC Functional tab, you can set exchange correlation functionals and van der Waals corrections. In addition, you can edit settings about charge, magnetization, GGA plus U, and isolated system. From Optimize of the menu on the bottom right, you can edit conditions of structural optimization. If you turn on the variable cell switch, the cell deformation in the structural optimization is allowed. If input fields are empty, you can set default values by the green arrow button. Then, I convert the crystal structure into primitive cell by modeling function. From the menu on the bottom left, I select Modeler function. On NanoLabo, you can convert the cell to primitive cell just by clicking the Build button of Finding Primitive Cell in Crystal tab. There are 2 silicon atoms in the primitive cell of diamond structure. If you want to understand that visually, you can translate all atoms by the slide bar of Transition of Cell in the Cell tab. The details of modeler function are introduced in another movie, so please watch it from the description. Besides, you can select whether to show mirror images of atoms on edge from designer function on NanoLabo. You can reflect the edited structure on each calculation setting just by clicking Reflect on Input File button. Setup of structural optimization of primitive cell of silicon single crystal is now complete. On NanoLabo, calculation settings you have to edit are minimized, and you can execute calculations immediately. Then, I execute structural optimization and visualize the results. I execute the calculation from the run of the menu on the bottom left. On NanoLabo, calculations can be executed on both local machine and remote server. I execute this calculation on local machine and set the number of MPI processes 2, and number of OpenMP threads as 5. By clicking OK button, the calculation starts. Running projects are displayed with red icon on the calculating screen. The structural optimization takes about 15 seconds. When the calculation finishes, the icon will turn green. Then, I open the result screen. On this screen, you can view the input file, log files, graphs, and movie immediately. In the input file, many calculation conditions are described. On NanoLabo, you don't have to make input files manually as before because NanoLabo generate input files from the settings edited via GUI automatically. In the log files, much information about the calculation such as results are recorded. On NanoLabo, you don't have to extract values to make graphs as before because NanoLabo visualizes the results instantly just by one click. This is the graph of total energy changes during the SCF calculation of the latest step of structural optimization. It can be seen that total energy converges as the SCF calculation proceeds. This is the graph of total energy changes during structural optimization. It can be seen that total energy converges as the structural optimization proceeds. Also, forces, stress, and lattice constants can be visualized similarly. Moreover, the movie of structure during structural optimization is available. For this calculation, it can be seen that the structure almost not changes because the initial structure is very close to the most stable structure. Also, just by clicking this button, the initial structure in the project can be replaced by the optimized structure. Finally, I calculate DOS and band structure of the optimized structure. I open the DOS of the menu on the bottom right. In the DOS, settings such as K-points and number of bands can be edited. However, default values have been already set automatically, so no change is necessary. Then, I execute the calculation from the run of the menu on the bottom left as in the structural optimization. The DOS calculation takes about 10 seconds. Then, I open the results screen. Just by clicking this icon, the result of DOS calculation can be visualized like this. Then, I execute band calculations similarly. I open the band of the menu on the bottom right. The symmetry of the structure has changed because of the structural optimization, so K-point's path and Brillouin zone is not set. In this case, K-point's path can be set automatically by converting to primitive cell. So, by modeler function of the menu on the bottom left, I convert the cell to primitive cell as before. Then, I reflect the change to the input file. The K-point's path is set automatically like this. Then, I execute the calculation from the run of the menu on the bottom left as in the DOS calculation. The band calculation takes about 10 seconds. Then, I open the results screen. Just by clicking this icon, the result of band calculation can be visualized like this. That's all for the first demonstration. On NanoLabo, beginners can execute band calculation of silicon single crystal for about 10 minutes like this. NanoLabo enables you to execute DFT calculations extremely easily and visualize the results instantly. Then, we show how to execute molecular dynamics of copper single crystal as the second demonstration. Firstly, I search and download copper structure file from the Materials project, an online database. Secondly, I edit crystal structure and set calculation conditions. Finally, I execute molecular dynamics and visualize the results. In this calculation, we heat the system from 10 Kelvin to 3000 Kelvin and then keep the system at 3000 Kelvin. Now, I search and download copper structure file from the Materials project, an online database, using Materials Finder on the top right. 9 structures, including only copper atoms, are displayed. I open the MP30, which has face-centered structure. Then, I save the project from the menu on the bottom left. Secondly, I edit the crystal structure and set calculation conditions. I change the solver to lamps from the menu on the bottom left. For this demonstration, I generate 6x6x6 supercell model by modeler function of NanoLabo. From the menu on the bottom left, I select modeler function. In Cell tab, I enter 666 in the input field of the scaling of supercell and click the Build button. Then, supercell model is generated like this instantly. Just by clicking Reflect on Input File button, you can reflect the edited structure on each calculation setting automatically. From the menu on the bottom right, you can choose Geometry, Force Field, Scheme, Option, and User Settings. From Force Field of the menu on the bottom right, you can select which force field to use. On NanoLabo, you can use classical fields such as Lennard-Jones potential, O+AA, Reeks-FF, Tursoff, EAM, MEAM, and neural network potential trained by advanced NeuralMD, and general force fields such as Open Catalyst and M3GNet as force field. For this calculation, I select EAM as force field. I click the Select Potential File button and select the EAM file of copper included in NanoLabo. Then, I set the calculation scheme from the scheme of the menu on the bottom right. The default setting is structural optimization, so I delete that by the cross button. On the right of the screen, details of each scheme can be set. As type of calculation, molecular dynamics, structural optimization, and structural optimization with cell deformation are available. For this demonstration, I select molecular dynamics. As statistical ensemble, NVE, NVT, NPH, and NPT ensemble are available. For this demonstration, I select NPT ensemble, in which volume change is allowed. I set time step as 0.5 femtoseconds, and number of steps as 400,000. I set the initial temperature as 10 Kelvin. And final temperature as 3000 Kelvin. And I keep pressure at 1 bar. Also, as restriction of cell deformation, isotropic, anisotropic, and triclinic are available. For this demonstration, I select anisotropic. The edited scheme can be added on the left of the screen by clicking Apply button. The scheme is added like this. For this demonstration, I also add the isothermal process at 3000 Kelvin after the heating process. I set number of steps as 200,000. And I set both initial temperature and final temperature as 3000 Kelvin. Then I click the Apply button, and the isothermal process is added after the heating process. On NanoLabo, several schemes can be executed in succession. On NanoLabo, you can calculate thermal conductivity, viscosity coefficient, diffusion coefficient, and radial distribution just by turn on these switches as needed. Also, from the option of menu on the bottom right, you can set application of electric field, external force field, fixed velocity of atoms, and deformation of cell as needed. These settings are applied to the atoms in the groups defined in the Group tab. Moreover, from the Users of menu on the bottom right, you can add any text into input file and define variables you want to calculate. We demonstrate how to use these functions in other movies of analysis cases, so please check them from the links in the description. Finally, I execute molecular dynamics and visualize the results. Then, I execute the calculation from the run of the menu on the bottom left. I execute this calculation on local machine and set the number of MPI process as 2 and number of OpenMP threads as 5. In the screen displayed before calculation, you can edit the input file directly to describe commands not implemented to NanoLabo. Even if the icon is red, which means calculation is in progress, you can view the interim results and movie of structure from the results screen. Degree of progress is shown here. You can open input file, data file, and log file here. Also, you can export the results as a CSV file. This is the graph of the potential energy. Similarly, you can visualize kinetic energy, total energy, enthalpy, temperature, pressure, volume, density, and lattice constants instantly. Moreover, you can watch the movie of the structure even if the calculation is in progress. Then, I check the results. From the log file, it can be seen that the calculation takes about 3 minutes. Then, I check the potential energy. The potential energy changes abruptly around 110 picoseconds. It can be interpreted as copper melts around 110 picoseconds. Then, I check temperature. Around 110 picoseconds, temperature reaches about 1500 Kelvin. Also, density changes abruptly around 110 picoseconds. So melting point of copper single crystal can be estimated as about 1500 Kelvin. Melting point of copper is known as about 1350 Kelvin, so the estimated melting point have sufficient accuracy as the result of calculation using classical potential. Then, I check the movie of the structure. I adjust the content reproduction position at about 100 picoseconds using seek bar. It can be seen that the crystal structure is kept around 100 picoseconds. Then, I adjust the content reproduction position at about 120 picoseconds, when temperature is above the estimated melting point. At about 127 picoseconds, it can be seen that the crystal structure collapses. If the movie can't be played smoothly because of many steps and atoms, you can save the movie as MP4 file by the Save Movie button. That's all for the second demonstration. On NanoLabo, beginners can execute molecular dynamics of copper single crystal for about 10 minutes like this. NanoLabo enables you to execute molecular dynamics extremely easily and visualize the results instantly. Finally, we show product information. NanoLabo can operate on Windows, Linux, and Mac OS. Calculations can be executed on not only local machine but also calculation servers or clouds. For NanoLabo, Trial Edition, Base Edition, and Pro Edition are available. Regardless of edition, you can use Jupyter interface for NanoLabo without extra charge until July 31, 2023. Separate license contract is necessary after August 1, 2023. NanoLabo Pro version 2.8 offers Interface Modeler and Polymer Modeler as additional functions. On Windows or Mac OS, node-locked license is available. On Linux, floating license is available. License prices are as follows. Please feel free to contact us for detailed information or demonstration. This is all for the movie. Please watch other movies and visit homepage from the description. Thank you for watching.